La diffusion vient de démarrer. Tous les participants sont en mode écoute seul.
Hello everybody. Hello, Matthew speaking. Hello, if you have trouble hearing me, please let us know in the chat. You should be able to hear me now. Okay, so hi everybody. Thank you very much for your time and presence today. I'm Matthew and I will be your contact here at PowerSys. Well, PowerSys, we are the distributor of this amazing tool that is PowerForge. So today we'll speak about how to reduce motor winding stress in MV drives. And for that, I'm pleased to welcome with me today Dr. Guillaume Fontes, which is the co-founder and the CSO of Power Design Technologies, the developers of PowerForge. Also, I'm pleased to welcome Mr. Professor Thierry Ménard, which is the scientific advisor of Power Design Technologies. So I wish you all a great time with us, and we'll have time for question at the end, of course. Thank you very much.
So thank you, Matthew, for this kindly introduction. So as you said, I'm here with my colleague Thierry Ménard to propose this webinar about reducing motor winding stress in medium voltage variable speed drives thanks to multi-level topology used to their full extent, as we are going to see it, that's to say, by increasing the number of levels. So first of all, let me say a few words about the field of medium voltage variable speed drives, commonly named medium voltage drives or MV drives. So variable speed drives are used in a wide range of applications in industry and transport, such as wind turbines, mining, marine and naval applications. So demand for these drives has been growing for a few years, especially at the megawatt level, that is to say, the medium voltage level, due to the increasing need for efficient motor control because of rising energy prices and environmental concerns. So in this context, a major use case is the retrofit of an existing medium voltage motor, originally powered straight from the grid, as here. Okay, so in this case, the introduction of a variable speed drive is very interesting because it saves the motor replacement, it increases the operating efficiency of existing motors, and it also increases safety. But as it used to be a motor powered straight from the grid, we need to be very careful about the stress of windings. Thus, in such cases, this often requires a bulky and costly output sine filter in order to preserve the motor windings from excessive current harmonics or voltage overshoots. So in most of cases, the use of a three-level inverter, such as neutral point clamp topologies or T-type topologies, is already a well-established solution. Yet, further increasing the number of levels to 5, for example, as shown in this figure, okay, can change the game by reducing the current harmonics, as shown here, okay, and so which can lead to significant filter downsizing. Okay. Moreover, okay, fast voltage transitions caused by the PWM waveform called voltage spikes that can damage the isolation of the motor windings. So here again, multi-level solutions reduce the voltage steps, thus reducing the spike amplitude. And at last, it also offers options such as cheaper lower voltage IGBT modules, which can lead to a global reduction of the cost of the global converter. So to sum up these two issues, I would say that increasing the number of levels in multi-level topologies for MV drive can reduce the current harmonics, that's to say the THD, and limit the voltage overshoots, and which leads to significant filter downsizing. Okay, so then we agreed on this degree of freedom. But okay, in my application, in this case, okay, how to consider such degrees of freedom, and which topo fits better to my application. Is it a 3-level topology, a neutral point clamp, T-type, or a flying capacitor, or is it a 4, 5, 7-level topologies? Okay, so depending on this topology, which switch reference do I need, and what about the switching frequencies? So this is the kind of question we can answer with PowerForge, the platform to help engineers to design their power converters. Okay, and that's why I propose to show you in this webinar. So indeed, let me remind you the workflow used with PowerForge. So we are going to explore the different degrees of freedom I mentioned above. That's to say, different topologies, different switching frequencies, and different switch references. And we are going to compare all these solutions. Okay, try to understand the advantages and the drawbacks of each solution, and eventually pick the ones which meets the best requirements. And afterwards, if we have time, we will show the potential of different exports, and especially an export to PSIM, in order to show how the designer can keep on his design process to another software. Okay, so here is the requirements of the example we are going to consider. So this is a medium voltage drive of a power of 2.4 megawatts with an AC voltage of 3.3 kilovolts and with a fundamental frequency of 50 hertz. And so to simplify, the analysis and the different comparisons, we have made the choice to consider a given and known heat sinks for all the different solutions. So here are the different solutions I propose you to consider. So we are going to consider two 3-level topologies with an NPC and a T-type with switching frequencies around 450 to 600, and with an ABB switch, with a rated voltage of 6,500. And then we are going to consider a 4-level topology with a flying capacitor, switching frequency of 600, and here another switch reference with a rated voltage of 3,300. And then we are going to consider at last 5 and 7 level topologies, with a stacked multi-cell converter, especially, and so which will use both 3,300 rated voltage switch, and at last switch from Dynex, with a rated voltage of 1,700. So here I tried to consider some prices for all these switch reference. So of course we have we must be careful about these prices. This is just to give an order, and of course these prices have to be customized with yours. So now I'm going to switch to PowerForge. So here is a project I've just created for this demonstration. So here are the specification range of this project, and here we've got a first design, with the NPC topology I've created. So let's go into this design. So this is the results dashboard of the design. So you can recognize here, the different switching cells separated by the two different filters, and here the cooling, and here the switching controller. So all these subsystems can be reached with the panel on the left. So first of all, let's go to the operating point. So here you can recognize the AC power, of 2.4 megawatts. The AC voltage of 3.3 kilovolts, and so on. About the switching cells, as I told you here, we have chosen the 3-level network point clamped topology. So with the ABB switch with a rated voltage of 6.4 kilovolts, okay, and then the price, okay, the order, the device I've chosen. So, and about about the switching controller. So here you can see the switching frequency, okay, the carrier type. So here we have chosen also a modulation strategy of third harmonic injection, and here a carrier disposition of phase disposition. So here we had two choices, the phase disposition and also the alternate phase opposition disposition. So what does it mean? So now I'm going to give the floor to my colleague Thierry, who is going to say a few words about the advantages and drawbacks of these carrier dispositions. Okay? So Thierry?
Yeah, thank you, Guillaume. Thank you, Guillaume. So yes, I will try to give you some simple comments to help you to understand some small tricks about modulation in three-phase converters. So basically, when we speak about carrier-based modulation techniques, we have different ways of using carriers. The most conventional and classical way of using multiple carriers is to have them horizontally disposed, as shown on the left of the slide. So basically, each cell will be controlled by a signal that is generated by comparing the carrier with a reference signal. And because the carriers are phase shifted, all the switching cells will receive a control signal that is with the same duty cycle, because it's related to the value of the reference, and with a phase shift that is imposed by the phase shift of the carriers. So it's quite easy to do that, and in general, it's what we use in DC-DC converters, in single-phase DC-AC converters, and it can also be used in three-phase voltage source inverters, but we will show that it is not the best way to do in three-phase converter, and I will try to explain quite simply why. So the other way to generate these different control signals is to use vertically disposed carriers, as shown on the three diagrams on the right of the slide, that are respectively APOD, POD, and PD. And you can see that the pattern is somehow different, but in all cases we have four carriers that have an amplitude of 0.25, and they are very vertically phase shifted. So I will not discuss all of these, but maybe if you, Guillaume, can you click, please? So if we look first on the behavior of a phase shift and the APOD, the first thing we can explain is that in fact it can give exactly the same result. As you see with this animation that it just showed, the pattern is exactly the same in these two cases. You can superimpose the overall diagram of these two kinds, and that means that in fact, although the carriers are different, you will generate exactly the same pattern with these two modes. So this is equivalent. Now, if we look at PD modulation, the one that is on the right, I will stress this one now because it is in fact the best choice. And why is it the best choice? Because if you look at the carriers, the property of the PD pattern is that all the carriers are in phase. And now, if you look at the point of operation with the black circles, you can see that I have shown now the three references of the three phases of the system. And you can see that on the PS block on the left, the triangles that will generate the control signals are not all with the same orientation. The two upper triangles, small triangles, are pointing towards the bottom, while the third one is pointing toward the top. And that means that the pulse that is going to be generated with the PS pattern is as a different phase shift. It's in fact phase shifted of 180 degrees for the last of the three pulses. If you look at PD pattern on the right, you can see that although the references are in different bands, all the pulses have the same phase. And in fact, this is a significant advantage because that means that the harmonics that are generated by the three phases are in phase. So in fact, they act like a common mode, and they cancel out in the line-to-line voltage, which is the voltage that is going to be responsible for the current distortion, for the THD, and for the losses, for the extra losses in the machine. So this is a simple way to understand why PD modulation is superior to PS modulation. In the literature, you will find a lot of other ways to justify the superiority of this modulation. It can be based and showed with heavy mathematics and with a comparison of THD waveforms, THD values. But I think this way of showing it makes it easy to understand. So as a conclusion, this is the kind of option that you have when designing the system. When designing the system, you can go for phase PS modulation or phase shift modulation, and it's quite easy to implement. Or you can make a slightly more difficult implementation of the control, and you will improve the content on the THD of the system. Next slide, please, Guillaume.
Yeah.
So this is another way to look at this comparison. In this case, you can see of this example of T-type and NPC. Next, please. Guillaume, yeah, thank you. So here you can see that for the different affiche tuva, for the different pulses, you can see that the phase shift has been inverted, and that also means that you have different losses for the cells in these two cases. Next, please.
Okay.
So this is a summary of the different types of carrier disposition that you have, and you also have some different cases to that are taken care of using PowerForge. That depending on the parity of your or the ratio of the switching frequency to the modulation frequency, you have some appropriate patterns. You have some appropriate pattern that is generated. And in some conditions, you can generate different losses for the top and bottom switches. And you can also generate even order harmonics, which are problematic for most of the nodes. So this is something that you can detect using waveforms and the spectrum that are displayed in PowerForge. So basically here you have a table showing the good combination that in case you use different combination, you will somehow be notified that you have this kind of problem in your design. Next.
And that's all. So okay, thank you, Thierry, for this information. And it's impressive how it can be simple. So now we have understood all these degrees of freedom. I propose you to go back to PowerForge. So here, as Thierry said, it's usually better, okay, to choose the phase disposition, okay, for the voltage harmonics that are produced. Okay, so now if I switch to the last subsystem, okay, so here in order to see the influence of the sine filter design, okay, we have chosen an auto designer of the sine filter, okay, which is still in beta mode, but it's just to have in order to have an idea, sorry, of the influence of the topology on the design of this this AC filter. Okay, so let's go. Okay, so now PowerForge is going to evaluate and to design each subsystem, first the macro cell, then the filters, then computed losses and design the coolings. So here we've got a small warning, okay, telling us that the current ripple is not really respected, okay. So here it's a little bit higher, okay, but not very important here. So here you can see we have the result dashboard. Okay, so here you can see the different breakdowns. So as we can guess, it, we have okay, a great contribution, okay, here of the AC sine filter. If we have a look at the mass breakdown, and here, if you have a look at the power and the cost breakdown, so here we can see the main contribution about the switching cells, that to say that the power switch for both the power loss breakdown and also the cost breakdown. Okay, so now, for example, let's try another topology and to see a little bit the difference. So I'm going now to consider a 3-level topology, but this time a T-type. Okay, so I go back to the macro cell subsystem and I choose a T-type. Okay, so now I'm going to use the same switch, which was, okay, the ABB switch at 6.5 kilovolts. Here we are. Okay, and okay, the cooling temperature was supposed to be 65, and we have to re-enter the cost by components, okay, which is 2050. Okay, here we are. Oh, I forgot to change the name. Never mind. I will do it afterwards. Okay, here we are. Okay, still the same warning message. That's okay. That's quite logical because actually we've got the same AC waveform. So now I prefer to choose another name. It's much more convenient to compare the designs. Okay, here we are. So here, so we have got the exact mass breakdown with the exact with the same contribution of the filter. Here you can see also an equivalent contribution of the losses. So here we can notice that the losses of the switching cells are a little bit smaller, which are a little bit lower than 16 kilowatts. Okay, in the NPC it was a little bit above 16 kilowatts. Okay, if I go back to this design, okay, in the NPC, okay, here we are. Here, yes, we have, sorry, a little bit above 16 kilowatts. So this can be also shown in the comparison space, just here. Okay, in these diagrams. So for example, here we've got a first graph, efficiency versus specific power, and efficiency versus power density. So here you can see the T-type design and here the NPC design. So here, as the losses are as a little bit lower in the T-type design, okay, the efficiency is a little bit higher. Okay, so maybe here we can increase a little bit the switching frequency. Okay, and that's what I'm going to do. Okay, so I go to the switching controller. I choose here a frequency of 600 Hertz. Okay, and I'm going to change the name. Okay, so here we are. So now, yes, here we are. So here PowerForge warns me, okay, because I've chosen a ratio between the switching frequency and the fundamental frequency, which is hidden here. And so, as Jerry told us, okay, this can be problematic, okay, for losses which are not symmetrical, and also for harmonics at twice the fundamental and 4 times the fundamentals, okay. But okay, so here, if we go back to the comparison, to the comparison space, okay, so here we are. Okay, you can see that with the increasing of the switching frequency, we have increased the specific power. Okay, but of course the losses are a little bit higher, so that the efficiency, okay, is lower. We can prove that, okay, with, if we want some details about these two designs, for example. Okay, and here we've got here the different breakdown for each solution. So we can notice here a slight decrease of the AC filter as we increase the switching frequency, and here we can notice, okay, the increase of the losses of power switches. Okay, so now let's consider another topology, to say a four level topology. Okay, with a flying capacitor. So here I go back to the macrocell subsystem, okay, and I choose the flying capacitor macrocell. Okay, so I'm going here to choose 3 cells in order to reach a 4 level topology. So here I'm going to choose another switch reference, okay, with a rated voltage of 3.3 kilovolts. Okay, here again, the temperature of the surface. Here I've got it's the voltage trace ratio, and so as we saw, the price of this component is much lower. Okay, 1.4. And I'm going to change the name this time of this topologies. So this is a 4 level flying capacitor, okay, and which uses a 3.3 kilovolts power switch. So let's go. Reforms, okay, done. The losses in the cooling. Here we are. Okay, so the first thing, okay, we can notice, okay, is the different, okay, mass breakdown. So here you can see that the AC filter, okay, has decreased, but that we've got now a contribution of the switching cells. This is because it includes this time the flying capacitor of these topologies. So now, if we go back to the comparison space, okay, so we can see this last topology here, okay, which is a little bit lower with the efficiency, but which offers, okay, a great specific power, which is not the case with the power density, okay, because of the volume of these different the flying capacitors. And about the cost, so about the cost, okay, so here with the prices which are quite approximative, once again, okay, with the prices I've chosen, okay, this solution seems to be very, very interesting, okay, because of the lower prices of the low voltage rated power switches. So it can be a good solution. So now I'm going to show you another topology, okay, which this time is a 5 level topology with a stack multi-cell converter. Okay, so here it is. so a 5-level. So I'm going to use still the same switch, that's to say the 3.3 kilovolt power switch from ABB here, with a cooling surface of 65 degrees, and so the same prices. Okay, and I propose you to check this topology at a switching frequency of 900 Hertz. Okay, so this is a 5-level topologies. This is SMC, and the switching frequency is 9 Hertz. So here we are. Okay. So design filter, cooling. Still this warning message. Okay, but it just doesn't matter. So here are the different breakdown, but let's go straight on. Okay, to design, to the comparison space. Okay, so here we are. So this was not a good option. Okay, to increase the efficiency, but once again to increase the specific power, that was not too bad. And here, about the power density because of the volume. Okay, because here we have fewer flying capacitors, so here the power density, okay, is much better than the flying capacitors. So what about the cost? So the cost, well, it's quite interesting, okay, compared to the 3-level topologies, but here it's not as good as the flying capacitor 4-level topologies. Yeah, that's all. So now, in order to show you the potential of getting cheaper low voltage IGBT, I propose you to switch to another topologies, okay, with 7-level stack multi-cell converters. Okay, so here I'm going to increase the number of flying capacitor stages, and so I'm going to choose another component, which this time is the Dynex, the component from Dynex. Okay, here it is. And so this component, so I've found a price around 400 volts. So here I've got to increase a little bit, okay, the voltage trace ratio in order to use it in this topology. And I propose you to evaluate this topology at 1,500 Hertz. Okay, as it's low voltage power switch, they can switch higher. And then of course unchanged name. So, and so this time, this is 1.7 kilovolts component. Okay, check everything because sometimes I forgot a few things. Here we are. So maybe it would take a little bit longer. Designing, coding. So, okay, here we are. Yeah, let's go to the comparison space. So now, yeah, here it is. Okay, we've got here the last design, the 7-level stack multi-cell with a switching frequency of 1,500 Hertz. So about the cost. Well, this solution, okay, is quite good actually because of the lower prices of the power switches. So if we want to be sure about that, okay, let's go some details about this solution. Okay, so here we've got the different breakdowns. Okay, so here you can see the cost breakdown of all these solutions. So and so as we can notice it, okay, the low voltage IGBT modules here are quite cheap, which makes the global cost of the converter much lower. So of course here, if the goal of the designer is to increase once again the switching frequency of to increase the specific power of the converter, he still try to increase the switching frequency. See, that's not a problem. Okay, because these components, these low voltage components, can switch a little bit higher. So, for example, if I switch to 3 kilohertz, okay, just change the name. Okay, still the same warning, doesn't matter. Okay, so you can see here that for if we have a look at just as the Mac breakdown, okay, and if you are still in mind, okay, the first Mac breakdown with the 3-level topologies, you can see that it's quite different. Okay, so yeah, so this is the last point. So here we have still increase the specific power, okay, but this has a price, okay, and the price is the efficiency here. About the cost, yeah, it's a little bit much cheaper, but that's not so much actually. And so here are the different contributions for the old design. So this is the kind of trade-off, okay, we can perform with PowerForge. So and when the designer wants to pick one of them in order to keep on his design process in PESIM, for example, this is possible. He can use the export features. So for example, let's choose the 7-level topologies, and if I want to export it in PESIM, so here I've got a zip file, okay, which I download. Okay, let's download it in the desktop. So here I just have to extract this zip file. Okay, inside this zip file I've got several files, okay, and just now I'm just run a script in order to build the main circuit, okay, and now I can open the main circuit, okay, which has just been created here, okay. And we can recognize, the 3-level inverters with inside, the stack multi-cell, the multi-cell converter. So I'm not going to simulate it because here it will take too long. But it's just ready to use. Okay, so it makes easier, the workflow of the engineer who wants to keep on his design process. So as I said, that's the kind of trade-off, we can perform with PowerForge. So, in conclusion, I hope I showed you how by increasing the number of levels in multi-level topologies, we can reduce, the THD thanks to the increasing of the apparent switching frequency. And another benefit of increasing the number of levels in that we limit the voltage overshoots. And at last, we can optimize the cost by increasing the number of levels, as we have seen. Okay, using cheaper low voltage power switches can be benefic to reduce the overall cost of the power converters. So if now you are ready to explore the full potential of medium voltage drive, and if you want to get started with PowerForge, do not hesitate. So you can contact us. Okay, so here are the different links. If you want to experience the live demo, do not hesitate. Okay, to go to these links, or if you just want to get in touch with us. If you want to just to get more information, just go to our website. So yeah, thank you very much. And so now Thierry and I are open to your questions if you have. Okay, so we don't have a lot of questions yet. So maybe we can start with a short comparison between the NPC and then the T-type, for example. We have at the beginning, okay, of this webinar, okay, we have seen that the T-type was a little bit better, okay, than the NPC in terms of efficiency. That the T-type, okay, has lower losses, okay, here that the T-type has lower losses than the NPC. So this is the T-type at with a switching frequency of 450 Hertz. And so this is the NPC. Okay. The NPC. Yeah, the NPC at the same frequency. So globally, in most of cases, the T-time will be better than the NPC, just thanks to conduction losses. So here, if we see the current path, okay, we've got three possibilities with the T-type topologies, whereas with the NPC, we just have, okay, two passes. So if we have a look, okay, at the conduction losses here, which are 580 watts, okay, they will be higher than in this case, okay. With here we've got only a little bit more than 400 watts. So that's usually a simple explanation to explain why the global losses are in the T-type are a little bit lower than in the than in an NPC topology. So yeah, we've got a question. So from Dino, who is asking me, how is it the filter damping down here? So I'm supposed that you're talking about the AC filter. So here as yeah, okay. So I suppose that here on the AC filter, as the frequency, okay, the resonant frequency of this filter is quite low. Okay, we assume that it will be handled by the control, by the regulation, the current regulation of the system. Okay, I know if Thierry, you wanted to add some precision about this kind of question.
Yeah, I just wanted maybe to point out that we have a question about the damping of the filter, and I'm not so used with the system, so I think it was answered, but I'm not sure.
Yeah.
So the question. Yeah. I just everybody on the damping of the filter.
Yeah, I answered that here in this filter there was no damping, and that we assumed that it was that it was handled by the regulation, that's the global regulation of the system, by the current regulation of the system. Okay, so we've got another question, okay, from Jabal. Is it necessary to use a specific modeling format on PSIM to get loaded in PowerForge, and is it possible to load circuit from another software than PSIM? So, so as we have a partnership, okay, with PSIM, we prefer that you load the circuit with PSIM. But for some topologies, okay, we also provide an export to Plex software. Which topologies? So this is you can find this on the user guide. So I'm trying to use.
Yes, but maybe Guillaume, I can add some comment, because I think the question was showing that there might be a little misunderstanding.
Yeah.
If you make a design for a project using PowerForge, then it's possible to check your design and to export it to PSIM. But I think the question was the other way around. If you do something in PSIM, can you export that to PowerForge? So I think we must be clear that this way is not working. We're not able to start something in PSIM and make some kind of optimization of the design in PowerForge. So I'm not sure if that was really the question, but that's how I understand the question.
Okay. Yeah, Terry, you're right. Thank you. Thank you very much for the precision. Okay. So here, the workflow is that the designer first uses PowerForge, okay, in the early stage design phase, and then he can export some files into simulation tools such as PSIM or Plex if he wants to. The other way, that doesn't work. Okay.
Okay.
Yeah, we have answered to the question. So maybe I don't know. We don't have any more question. So
I don't think so.
So I don't know, Terry, if you wanted to detail some design comparisons, as I just made between the T-type and the NPC topologies.
No, I think maybe just we can add the little comment that you started making the comparison between the NPC and the T-type, and maybe it's nice to stress that the SMC, the stacked multi-cell converter, that is available in PowerForge and that has been used in industrial products. It's also another way to get this advantage of having 3 paths for the currents to flow, which means that you have some kind of reduction of the RMS current flowing in each of the semiconductors. So that's basically a nice topology when you want to increase the power that you can handle. And if you take a given module and you increase the current until you reach the power limit temperature of the module, then you will be able to take more power out with a stacked multi-cell, because it's, in a way, it can be considered as a topology in which you have some series connection, of course, because you have devices that share some voltage, but they also share some currents between different cells. So it can also be seen as some kind of paralleling of devices. And it's a nice feature that we can explain quite easily. But then if you have a tool like PowerForge, you can really put a figure and say okay, in that case, with this module switching at this frequency, I can see that I get, for example, 15% more voltage, more power out of my system.
Yeah, that's why I think. So thank you, Terry, to underline these similarities of current passes between the stack multi-cell and the two types. Yeah, that's a good thing. Yeah, we have another question about is any motor parameter considered as well for the design, like minimum? Then see. Like a minimum leakage inductance. So yeah, this is a feature which is coming in the next release, and so this feature will be ready for the PCIM conference, okay, which was in Nuremberg, so in the beginning of May. So yeah, so we are going to consider a simple model for the motor, okay, with a leakage inductor, a resistance of the winding, and an electromotive force, and so this feature will be available at the beginning of May. Okay. Okay, so third question. Okay, so here we are. So once again, thank you for your attention. So if you don't have any more questions, maybe we can close this webinar. And so do not hesitate to get in touch with us, and so to go on our website. So the video of the webinar, a YouTube channel. Okay, if you want to see specific details that you may miss during this webinar. Okay. Okay, so thank you very much.
Okay, thank you, Guillaume. Thank you, Thierry, and thank you everybody for your presence and your time today. For any commercial inquiries, you have my email address into the chat. I pasted just before. You can have a 15 days evaluation when you want, and we can go further on other topics if you would like with a private meeting. So feel free to reach out to us, and have a great day, everybody. Bye.
Bye-bye.
Bye.